Hello. In the previous video, an equivalent of this image was shown. It was a chip engraved on a film made of a flexible plastic material with conductive tracks. This technology is known by the acronym COF, which is an abbreviation of chip on film. The small circles in black correspond to test points. They are not directly accessible because they are covered with an insulating material which must be removed if we want to access the conductive part. To know the name and the function of each test point, it is necessary to note the name of the chip registered on the COF and to find its datasheet. Here, we are interested in the chip that drives the rows called gate driver. The name of each test point is given in abbreviated form whose meaning will be detailed in this video. We see in this example the location of two COF of gate driver placed on one side of the screen. The plastic material used is made of a polyimide, which one of its characteristics is to be thermostable. It does not vary during 1000 hours at 300 degrees Celsius or during 10 hours at 400 degrees. As it is flexible, this technology is also called chip on flex. Some screens, especially those of the last generation, do not have a COF gate on the sides. This does not mean that the screen does not have a gate driver. On the contrary, the chips exist and they are integrated directly into the panel as for TFT transistors or storage capacities. This technology is currently favored in the manufacture of screens and it has several names. We find COG, which means chip on glass, GIP for gate driver in panel, or GOA for gate driver on array. The gate drivers are used to drive the TFT through their gate. They control the passage or not of the voltage that feeds all the gates that are on the same line. The transistors are in on state when their gate is supplied with VGH. They are in off state if their gate is subjected to VGL. A technical precision concerning the mode of manufacture of transistors TFT, which is the acronym of thin film transistor. There are mainly three modes of manufacture of TFT. Each technology has its advantages and disadvantages. The most widespread and oldest technology uses hydrogenated amorphous silicon material. Another technology, called EXO, which is the abbreviation of materials used in the manufacture of TFT, and which are indium, gallium, zinc, and oxide. The advantage of this technology is that this alloy allows more light to pass through, which reduces energy consumption by reducing the light intensity of the backlight. On the other hand, the size of the TFT in EXO are smaller, what allows to put more pixel in a panel where an improvement of the display resolution. The third technology is called LTPS, which acronym of low temperature polycrystalline silicon. LTPS has the same advantages as EXO, and in addition it allows to integrate the electronics with each pixel. Now, we are going to tackle the heart of the matter, namely the internal electronics in a gate driver chip. This chip contains a succession of electronic functions cascaded one after the other. Thus we find a shift register, a logic control, a level shifter, and a buffer. The shift register is an assembly of several electronic devices called a flip-flop. There are several models. Here will be used the flip-flop D. It has two inputs. A first input for the data named D, like data, and a second input, T, for the time controlled by a clock signal. The D flip-flop has two complementary outputs, one called Q, and the other Q bar, which takes the inverse value of Q. The operation is relatively simple. The value present at the input D, 0 or 1, is transferred to the output Q under the control of the clock, T. Depending on the setting of the flip-flop, the exact moment of transfer is made either on the rising or falling edge of the clock. The rising edge corresponds to the moment when the clock signal passes from 0 to 1. The falling edge is the opposite. Here is the table of operation of a D flip-flop. When the input D value is 0, the up arrow means rising edge of the clock. The output Q will be equal to the input, so 0, and Q bar is the opposite, it will be 1. When D is equal to 1, Q will be equal to 1 and Q bar will be at 0. The configuration of the shift register is done according to this diagram. Several flip-flops are connected in series. The output of each flip-flop is connected to the input of the next flip-flop. The information or data enters serially into the first flip-flop and leaves serially from the last register. The output of each flip-flop enters the next flip-flop, but the information also takes a second path which is parallel to the outputs of the other registers. Q1 coming from the first flip-flop constitutes the input of the second flip-flop. The output Q2 will be the input of the third register, and at the same time it will constitute an output which will go up in parallel to Q1. And so on. This assembly allows to store a binary data. In the gate driver, the D of the data will be the signal that allows the scanning of the lines to begin vertically. In short, it is noted STV, which is a contraction of start vertical. It can be found under the abbreviation VST, which is an inversion of the previous words, which gives vertical start. STV or VST is the V-sync, which is abbreviation of vertical synchronization. For the clock signal, the T is replaced by CPV, which is a contraction of the words clock pulse vertical. The following animation shows how the information flows from one flip-flop to another in series, but also out of each flip-flop in parallel. The shift register used in gate drives is often bidirectional, i.e. the information can flow from left to right or vice versa. STV is the signal of the beginning of the vertical scanning of the frame. CPV is the clock signal, which allows to synchronize the output of the data of each flip-flop in a successive way. On datasheets, there are different ways to specify the direction of operation of bidirectional registers. For example, for STV, which is the abbreviation of vertical start, we add a number to STV. STV1 will indicate the direction of the scan from left to right, and STV2 for a scan in the opposite direction. We can find another denomination like SVIO or SVOI. SVOI is the abbreviation for start vertical input output, i.e. a scan from left to right, and SVOI is the start vertical output input for a scan from right to left. Another term, DO, for data input output, or DOI, for data output input.